I think following our last class's discussion about nomenclature, one thing that I wanted to clarify was what the principal functional group means. And I think, honestly, the list that I gave you for suffixes, it gets a bit confusing. So remember that our suffixes are ein, een, ein, or the combination of een and ein. And we can stopper these suffixes with another piece of information. Even still, these functional groups fall into the priority list. So if your compound has a carboxylic acid, the reason we call it principal is you want that to have the lowest locant possible. That's the idea. On your parent chain, give the carboxylic acid the lowest locant possible. And a carboxylic acid is a terminal functional group. So it will always be position 1. Esters are the same way. Esters are terminal, so they'll always be position 1. And keep in mind that this list is unique to our class. It's not comprehensive of all functional groups, but I'm not going to have you name all functional groups. After that, we had aldehyde and ketones. Which are tied in priority, but when both are in the same compound, aldehyde takes priority. Why? Equal electronegativity. Oh, it is more electrophilic, but that's not why the aldehyde is primary. It's actually not alphabetical because I won't have al-one in the suffix. I can only have one suffix stopper. Were you going to add anything to that?
It's on the end.
Same thing, yep. The aldehyde will always be carbon 1. The ketone will never be carbon 1. So if we're looking for the lowest locant set for the principal functional group, you'll start with an aldehyde and make the ketone the substituent rather than looking for the ketone and making the aldehyde the substituent. After this, we said that we had alcohols. And then lastly, this is where I should have reminded you that alkenes and alkynes fall into this principal functional group. They just are the suffix, not the suffix stopper. So it's a good thing to remember because if, for example, you have a molecule that has both an alkene and a ketone, whose locant do you want to minimize? The alkenes or the ketones? The answer is a ketone. And the fact that alkene and alkyne are equal in priority, what happens if there's a tie? Or, sorry, the fact that they are equal in priority, and I don't have to make one of them a suffix, a substituent, excuse me. They can both show up in the suffix. That means that I can look to minimize either one's locant set. Try to get the locant set lowest for either the alkene or the alkyne. But if it's a tie, it doesn't matter which direction, both the alkene and the alkyne have the same locant set, then we go alphabetically. Een comes before ein. All right, anybody want to describe how they would name this first compound? Where will you start? How will you number? Start at the ketone. You don't have to say 1-one. In a ring, it's always assumed that you're starting at the principal functional group. And number which way? Clockwise. Why? Now we want to get the lowest set for the alkene, which means I'm considering that alkyl group last. So if we were going to add anything more to our list, we would say alkyl groups and halo groups are the last thing we prioritize in naming. So that gives us the alkene at 1 I'm sorry, the ketone at 1, the alkene starts at 3, but I don't say 3 and 4, and it gives me 5, 5 for my 2 methyl groups. 5, 5 dimethyl cyclohex 3-enone, or you could call this 3-cyclohexenone. This is one of the few times you don't have to describe the locant of the ketone. Typically, a ketone in a linear chain, you need to say what carbon it's on. Anyone want to reiterate why I don't have to say 1 is where the ketone is here? Because it's a ring. Because ketone is the highest priority in this ring. What other carbon would I start on? I would always start where the highest priority is, in a ring. But in a linear chain, I start at an end and I name through the chain. Okay. The compound to the right, what is the principal functional group? Ester. And what is the longest carbon chain containing the ester? Propyl. Remember that with esters, we name this alkyl ester linkage first. So our name starts with ethyl. And then we actually name the rest of it with the same wording we would use for the conjugate base of a carboxylic acid. How do we describe this benzene ring? What locant? 2-phenyl. So I know my carbon chain is prop. What suffix do I choose? Ane, ene, ine, or enine? None? I need a suffix. Yeah. I need a suffix. If there's no alkene, there's no alkyne. Then I use ane, and I cut off the E, and I swap in O8. Propanoate. Propanoate. Okay. What's weird about it? Would you have called it?
I would have said phenyl, ethyl. I would have said methyl.
You would have named this as a methyl substituent?
Phenyl, ethanoate,
1-methyl 2-phenyl propanoate. Right. Calling that's actually part of the reason why I drew it as weird as I did. It's because I didn't want this to seem intuitively like part of the longest parent chain. I wanted to point out that the parent chain is whatever the longest chain you can find is. So if you're going to make a methyl substituent off of your last carbon, that's actually just a longer carbon chain. All right, anybody want to name this one? Good. So we describe these alkyl groups connected to the nitrogen as N, just to make sure that we know they're not connected to the rest of the carbon chain. And this is that 1-carbon aldehyde, a 1-carbon carbonyl structure. So it's going to get the root form and the suffix amide. But that's not the only name that this can have. You could also call it NN-dimethyl. Form is a common name. So what systematic name could I use to describe the longest parent chain? Meth. Suffix. I need a suffix. I can't say methyl. I need a suffix ane, ene, ine, or enine. Methanal. I'll use ane because there's definitely no alkene or alkyne. So that's methan, and the suffix stopper for an aldehyde. Oh, I'm sorry. I don't know what I was saying. I was thinking of Formaldehyde. Sorry. Methanamide. Is that what you said? I was shooting you down. I'm sorry. Methanamide.
Formamide is that H2O group?
No. Or yes. Formamide would be if this was NH2. Form is this. Just that one carbon carbonyl. So we can have formaldehyde, formamide, formic acid, formate. All right, now my last one. What is my principal primary group? So I'm going to start numbering from the carboxylic acid out. How do I name a ketone at a substituent position 5? Oxo. So I've got 5-oxo, hex 3-enoic acid. Once again, I could also call this 5-oxo 3-hexenoic acid. I forget who asked all of these topics. Any follow-ups on nomenclature? Okay. Also, somebody asked about the stereochemistry on active. Anybody remember whose that was? Because I'll want to pull up the active so we can look at it together. I think let's take making organometallics and epoxides, because those kind of go hand in hand. We have 2 categories of organometallics and 3 specific names that we use. The 2 categories were strong nucleophile and moderate nucleophile. What were the 3 types of organometallics? I know you all know one of them. Grignard. Better called? I'm not even going to write it out. Organomagnesium halide. Organolithiums. Imbuli is a good example of it. It's definitely not always Imbuli. And our last one, cuprates. Yeah, and the less effective name, Gilman. Good. RTCULI. Oops, I put this wrong. Although its full legal name would be lithium diorganocuprates. Cuprates is a good way of remembering it. All right. Let's show how we could form an example for each of these. For Grignard, an example that those of you in lab this semester did yourselves was you took bromobenzene, reacted it with elemental magnesium, and you made phenyl Grignard. This is a good reminder that it doesn't matter what the halide is attached to, sp3 or sp2, that halide can be substituted into an organometallic. Since you brought up Imbuli, let's show how we could make Imbuli. I'll need to start with some 1-halobutane, like 1-iodobutane. And is it appropriate to write it as this? React it with Li. What do we need? Nope. 2. We need 2 equivalences of lithium to do the same thing that 1 equivalence of magnesium does. Why do we need twice as much lithium as magnesium? Valence electrons. Lithium is a 1 electron reducing agent. Magnesium is a 2 electron reducing agent. And we need a 2 electron reduction here. With Gilman's, we start with organolithiums and add half an equivalence of copper iodide. Although this is the part where I would be happy to accept just copper iodide because it's really strange to write half an equivalence. Reason being, I need 2 equivalences of the organo group to bond to 1 copper. And then I can simplify it by putting the copper-carbon bond in the parentheses and putting a subscript 2. Good refresher? Yeah. I wouldn't show you fluorine, but if you gave me fluorine in a reaction, I wouldn't take points from you. Anything else that you wanted to review with making these? Yeah, isn't it kind of strange? If I had half an atom of copper, how do I get a full atom of copper? Another way of saying this is for every 1 equivalence of copper iodide, I need 2 equivalences of the organo group, or 1 equivalence of the organo group to half an equivalence of copper iodide. That's why it seems unbalanced, right? It's because I'm actually taking half of this, but showing a full equivalence at the end. All right, let's see how to use these in epoxides because they can be quite effective in epoxides. Epoxides tend to have 2 ways of reacting: nucleophilic conditions and acidic conditions. In acidic conditions, the epoxide becomes protonated, which changes its regiochemistry. In fact, this protonated epoxide starts to stretch whatever bond it has to the more substituted carbon, essentially transferring part of that positive charge to the more substituted carbon. And why does the positive charge go to the more substituted carbon? More stable there. It'd be less stable on the less substituted carbon. So in acidic conditions, epoxides are attacked. I'm actually going to show this not as a negatively charged nucleophile, but just as a lone pair on a nucleophile. Epoxides are attacked at the more substituted position. And I think the way that we said this in class threw off a few of you because there are 2 ways that you can try to remember this. In acidic conditions, the alcohol forms less substituted. In acidic conditions, the nucleophile adds more substituted. I like to think about where the nucleophile adds, and I know some of you like to think about where the alcohol will go. So find whichever one works better for you. So in this case, my product would be nucleophile added at the secondary carbon and alcohol added on the primary carbon. What could that nucleophile be? Could be, it can't actually be anything. Could be an alcohol. Could be water. It could be a bromide. Actually, it is locked in that stereochemistry. The epoxide either sits on top or underneath the carbons. And so wherever the nucleophile comes in, it's coming in opposite of where the epoxide is. Yep. So a backside attack. So in acidic conditions, we can see something like an alcohol with acid or a water with acid. It's less common, but we could show HBr, which would be bromide with acid. Below? How do you mean? What do you think?
But I think it's possible.
A resonance structure of what? So this epoxide that you're showing has incredibly strained bond angles. The sp2 carbon wants to have bond angles at 120 degrees. The sp3 wants 109, and this triangle is already squeezing the sp3 tetrahedral carbons. It's squeezing the sp2 even more. So I'm not going to say it doesn't exist out there, but it's not something you'll find. All right, so let me ask this. Could I show methyl Grignard with acid? Could I show this methyl Grignard with acid in an example of an acidic condition reaction? Right. You could show it, you would just lose points. Because the Grignard, the organolithium, the cuprate, these are strong bases. Those are carbons holding electrons on their own. They want to share the electrons, and hydrogens are a great place to share them. So this is something I've seen before where students try to get a Grignard to attack the more substituted side. It doesn't exist. Click Santa. Sorry. Now, in nucleophilic conditions, this is where I have no proton source. So this would be like alkoxide, hydroxide, and this, also cyanide. I think one example I gave you guys in class was hydrogen cyanide. Acidic conditions, cyanide, nucleophilic conditions. This is also a great place to add your organometallic reagent, because organometallics can never be considered acidic conditions, always considered basic. Water is an acid to a Grignard, absolutely. You'd be surprised by the things that would be an acid to a Grignard. If it has a lower pKa, exactly. Which means that hydrogen gas, H2, has a lower pKa than an sp3 carbon. So if you had N-Bule, you remember in OChem 1 when you ran hydrogenation of an alkene and you saturated the fatty acid? If you had N-Bule in that reaction as the hydrogen is coming in, you would deprotonate hydrogen. And do you know what that makes? Deprotonated hydrogen. No, H plus is taken from H2.
Oh,
H minus, right? Which is not something easy to form, but that's how strong of a base these guys are. They can take hydrogen away from H2 and leave H minus, a weaker base, hydride. Now, where will these nucleophilic conditions attack? Will they attack more substituted or less substituted? Why? Because it's just the opposite. Yep. Process of elimination works great. But thinking back to your OChem 1 fundamentals, what is it about the less substituted carbon that a nucleophile would have a lower energy of activation attacking there? Sterics. Less steric strain. On this less substituted carbon, we have less things going on, which makes it easier for your nucleophile to access that position and open the bond. One thing that I may not have done well in class and in this example is the fact that this step will not give you a protonated alcohol. It leaves you with RO minus, meaning if this is your first step, adding some basic nucleophile, and you want to get an alcohol, you need to add an aqueous workup, H3O+. And in lab, we call aqueous workup washing, extractions. You're using that aqueous workup to protonate things and then take out any insoluble, aqueous soluble junk that you don't want there anymore. Step 1, left you with this, which is why we add step 2 to give you that alcohol. So here's the challenge about trying to make a ketone there. It's not taking a hydrogen from carbon, because carbon then would keep the electrons, and carbon has no one to share them with because oxygen has a full octet. You'd actually want to share oxygen's electrons with carbon, which would mean getting rid of H minus. So a reagent like CrO3, chromic acid, will, I think, use some radical intermediates even, maybe not, but it can kind of add and remove electrons more slowly, more readily, but more appropriately. There wouldn't be a base that you could add in, no. You'd want to add an oxidizing agent, something that will pull electrons out of that whole system. No, step 2 is just protonating. He's asking, is there a way that you could take that alcohol and make it a ketone? PCC or chromic acid. All right, Killian, did that cover your questions on epoxides? Well, I mean, there's acidic conditions or there's basic conditions. It's not really acid-base. Acetals? No. Acetals are reactive to carbonyls, aldehydes and ketones. But acetals, here, they don't have any reactivity. Okay, I mean, you can't make an acetal out of it. You could react an alcohol with them, but it wouldn't leave you with an acetal. Because remember, an acetal is the geminal diether. And here, you've got 2 carbons, not just 1, that are involved in the reactivity. Okay, no one's claiming the stereochemistry? Yeah, bummer. Well, it wasn't very big anyways this semester, was it? Stereochem. Do we need a refresher on chiral carbons? Okay, I think you guys are probably pretty good. It usually comes up once on the exam as is it a chiral structure? Actually, why don't you answer this one? Which of these structures reacts with methyl Grignard to create a chiral alcohol? To make a chiral alcohol. Okay? Methyl Grignard to make a chiral alcohol. So yeah, I'm just saying, like, take this. Which of these reacts with methyl Grignard to give a chiral alcohol? All in favor of the middle? Any in opposition? Okay, well, that's a point the entire class just lost on the exam. It's none. Yeah. So here, there's no chiral carbon because there'd be symmetry in the ring. Here, it wouldn't be a chiral carbon because it's already connected to a methyl. Now it has two methyls. And here, once again, there's symmetry in this chain. I didn't do that on purpose, but it was a good learning moment for us. Just added like a different carbon chain in the middle one on the left side. Should we see if these guys can get it? Did you guys miss this question completely? Mm-hmm. Don't give it to them. Which of these structures reacts with methyl Grignard to give a chiral alcohol? Yeah, no pressure. It's fine. The middle one. Okay, yeah, the whole class lost points. Great. Jamie? You just erase carbon 1 from the 3. Now it would be correct, correct. Okay, so the answer was none of them. It was a trick question. Yep. Well, you know, on the exam I'd have an answer that said none of these. I just didn't set you up for that verbally. No chiral carbon will be made. No chiral carbon will be made. The products will still have symmetry. But this one also has a methyl group already, so it'll just get two methyl groups at that carbon. Jamie's got a good point, though. If I shorten the chains here, if I change a chain here, and even here, if I turn this into an aldehyde, now each of these structures will make a chiral alcohol when reacted by that acyl addition. What's the best way to answer this? Sketch them all out, right? And then just go through your rules and say, do I have two identical groups on any of these products?
But the second and third, both three. I guess I wouldn't say it would be an S or an R, but you have to have the wedges.
Oh, I mean, the question is, would it make S or R? It'd be both 50-50 in enantiomers. Unless you could introduce some sort of chiral reagent to try and help you mitigate that. All right. Oh, that was the wrong one. Well, let's talk about condensation, multi-step synthesis. Your question, right? It was your question? No, that one's also up here. Was your concept kind of around like the unit test questions? Why don't we look at kind of the highlight reactions that we learned in Unit 5? First, we learned about alpha bromination and alpha alkylation. Then we looked at aldol addition. Although, to be fair, I tend to lean more towards aldol condensation when I give examples of this, because aldol condensation gives a product that can then react by Michael addition. So it lends itself really well to multi-step synthesis. We saw after that Claisen condensation. And then this problem, it's something that actually someone pointed out to me on Active, this problem with naming, which is what functional groups are allowed in what names of reactions, right? It seems not clear enough. In class, we said the Dykman condensation is an intramolecular Claisen condensation. But if I have an intramolecular that doesn't involve two esters, is it still Dykman because of the product it gives? Or does it have to have esters involved? It's not clear to me, which is why a lot of times I don't even put those names into the exams. These all kind of connect to, oh no, there was one more. Michael addition. I'm not saying Robinson annulation, mainly because Robinson, is that what you asked? Mainly because Robinson annulation is the Michael addition followed by an intramolecular Claisen condensation. Another thing I wanted to point out is that the Claisen condensation is a great precursor for alpha alkylation. Because the Claisen condensation gives you more or less. I have to say more or less because it doesn't have to be an ester. It could be a beta keto ketone. But this central alpha position is really good for doing alpha alkylation. You should know the aldol condensation, the Claisen condensation. Just those. Mm-hmm. The multiple choice questions will have intermediates, products, reagents necessary, those types of questions, yeah. And then sometimes the multi-step synthesis will, oh, there is another one. Maybe there's one more we should add here, which is the one I like a lot. What did you say? No, it's not what I was thinking of. Well, the crossed is just like, these are the main categories, but you can mix what's the nucleophile, and then that changes what is the product. No, decarboxylation. All right, I think I see a multi-step synthesis forming in my head, and I'm going to try and get it out of my head. Sorry? Sorry? The what? No, I'm not sure who you're talking about.
Bromination, that's a great reaction.
Okay, I've got to Wow, it's so pretty. I don't know how to reply to that. Thank you. I think. Do you see it? What are my rules on retrosynthesis? I mean, multi-step synthesis. What are my tips? Work forward and backwards. Don't get stuck just trying to go one direction here. Try to give yourself a hint by coming backwards. What else? Number your carbons. Yeah, map your carbons. Can you see where these might be in here? Can be hard. Trying to make sure I didn't screw up. I think I'm missing a carbon. Yeah. I think I am missing a carbon. Actually, two. I think it would be this carbon and this carbon. So I added a carbon on the alkene, and I added a carbon just past the alkene. Try not to introduce organometallics in the presence of a carbonyl, because organometallics will preferentially attack at the carbonyl carbon. Can we work backwards? I think this was a great one to try and work backwards from. What functional group do you see? Be more specific. It's an alpha beta unsaturated carbonyl. The carbonyl's alpha and beta positions are unsaturated. You can also call it a conjugated carbonyl. So if you wanted to say it's an alkene, well, first of all, remember that that's not our principal functional group. Try to look for the carbonyl. Then, if you are going to look at the alkene, look at how the alkene is positioned relative to the carbonyl. It's conjugated to it. Which of our reactions makes that functional group? Can you undo it? Yeah, you can do that.
What is this?
That's called aldol condensation.
There's two aldol condensations?
Well, you see the difference between them. One is basic conditions and one is acidic. That's right.
You can do it regardless.
You can do it regardless. Do you guys want, you're all working very hard. You want time to keep solving it? Oh, okay. By the way, I wanted to point out something. This is the final exam at CU Boulder. This is page 1. Draw the synthesis, draw the mechanism for this Robinson annulation. Fun, right? 30 points out of 100. Here, oh, actually, I guess that's not all of page 1. You also have to answer these. But we're not learning about amines. Here's another one. Show the mechanism for NAS. Hey, easy. You guys are good at that. And explain why one fluorine substitutes faster than the other. They do a lot more on sugars than we do as well. And then here's their multi-step synthesis. Make these compounds using at most 6 carbon atoms or triphenylphosphine or any transition metal catalyst. Yeah, they do a lot, right? They do a lot. So I know, I guess I kind of wanted to give you some perspective. I know you guys are coming in and you've got a lot of multiple choice problems that you have to answer, and synthesis, and roadmaps, and mechanisms. But it could have been this. Yeah. All right, let's solve this problem together. I'm going to start with a retrosynthesis because we learned how to break apart an alpha-beta condensation product. Alpha and beta is the bond I'm trying to make in this step. So alpha and beta is the bond that I will break in this step. Beta is what? Beta is a carbonyl. Now, I don't know, did you see this, that the product was 2 equivalences of the same chemical? You saw the similarity in the bonds, the groups. One question that I suspect you should have is, if you were mapping your carbons, did these 3 carbons take from the carbonyl to the left, or did it go from the carbonyl to the right? And if you're not sure about how to map your carbons straight away, then maybe try doing some brainstorming, some forward and backwards working before you try and map them. I actually would not know quite yet just which way is the best way to map them. What reagent can help me get here? LDA would be great. I would want half an equivalence of LDA. If I used NaOH, it will go to the more substituted carbon and make an enolate there, which means that I would only be able to run aldol addition. So it's possible that with hydroxide and heat, I can drive it to the condensation product. This is the only condensation product left. Condensation requires 2 alpha hydrogens be removed. And so alpha positions with less than 2 can't do condensation. You could, yes, you could just use H3O plus because H3O plus prefers that condensation product. All right, now what I see is an ester becoming a ketone. And I want us to stay in the context of this chemistry. There's actually more than one right way to get there. Back in Unit 4, we learned that esters can react with Grignards to make alcohols. But generally, it's 2 equivalences of the same Grignard that will attack. Because first, the Grignard will attack and then kick off the ester linkage and create a ketone. And then the ketone gets attacked because the ketone is even more electrophilic than the ester in the first place. So it wouldn't be great to try and take this to a ketone by Grignards because it's not going to let us add unique equivalences of different things. Instead, if I want to add carbon groups to my molecule, I might want to try doing it by alpha alkylation. And as we said, alpha alkylation is done best when we have these beta keto carbonyls. And so I could run a Claisen condensation before I do alpha alkylation. Can anyone name the beta keto ester that forms from this Claisen condensation? Yes, you can. Just have to know what it looks like. What reagent would you want to use to do Claisen condensation? Use the base that matches the ester linkage, or you could do, again, half an equivalence of LDA. One of these esters will have its ester group kicked off by the alpha carbon of the other ester. Now it might be easier for us to map our carbons. I'm gonna add a little bit more detail here in case that didn't quite clear it up for you. Let's say that this equivalence of the ester becomes the nucleophile, and this equivalence gets attacked. That means my alpha carbon is attacking beta. So here's alpha, which has now bonded to beta. Beta has been substituted. Beta has lost its ester group. Can you see how to map it? This one? Claisen condensation. It's actually not an acetoacetate because this carbon chain is too long. This would be 2-methyl acetoacetate because remember, aceto means a 2-carbon carbonyl. So the acetoacetate is a 2-carbon carbonyl substituting a 2-carbon carbonyl. But this is actually a 3-carbon chain coming off of it. So a better name would be 2-methyl 3-oxo pentanoate. Methyl 2-methyl 3-oxo pentanoate. All right, here's how I'm going to map it. This ketone position obviously is this ketone position. I need to have a 2-carbon chain. All right, well, there's a 2-carbon chain. And then another 2-carbon chain. Well, that's another 2-carbon chain. But I also want to have this phenyl group coming off of one of the alpha positions. So do you think I can get that, I should say benzyl. Can I get that benzyl group connected to this alpha position, or can I get that benzyl group connected to this alpha position? Well, this is set up perfectly for alpha alkylation. So I'm going to say that this is 2, 3, which means I'm looking at 1, 2, 3. And then, of course, I've got this, maybe I can call it 1', 2' on the other side. So I can do alpha alkylation, but I also have to get rid of that ester group. I need to go from having a beta keto ester to having a ketone. Let's do alpha alkylation first. How can I do alpha alkylation? To add this benzyl group to carbon 2. So you want to do you want to do radical halogenation. the phenyl group or the benzyl group connected? Yeah? Good. OMe minus. Have that base deprotonate the central alpha position. Makes a good nucleophile. Nucleophile attacks benzyl bromide and does substitution. Carbon 2 attacks this benzyl chain. What's the last step? How can I connect my two routes? Heat and acid. Because I need to hydrolyze the ester into a carboxylic acid, and then the heat will decarboxylate. So H3O plus and heat.
Add a bunch of acid and naphtha and the product.
Yeah, you might. Maybe. Christina, was that a good multi-step synthesis for you? All right, I want to come back. Do you remember earlier I messed up and I needed to add 2 carbons? I added a carbon to the end of the chain here, and then a matching carbon here. This is what I did wrong in my head. I knew I wanted to give you alpha alkylation and then decarboxylation. And what I did was I had this original carbon chain of the ester mapped here, but actually this original part of the ester maps onto the other side. That was a tricky part of that synthesis. If I maybe had written it down first, it would have been easier. What helped us solve that the best? Mapping? Yeah, backwards and forwards helped us solve it the best. Okay, let's look at some of the Unit 4 questions. Were there any in particular? Like Part A, multiple choice? No, it was all Part B, wasn't it? Yes. Okay. And for the sake of my class well-being going forward, I might actually this isn't what I want. I might not do the exact problems on the board so that they're not on YouTube forever. I mean, someday it won't even matter. I'll be gone. Oh, sorry, wrong bank. What was that?
Bottom step was decarboxylation.
That's right. Hydrolysis and decarboxylation. Sorry, you said you wanted to start with? Yeah. Okay.
For the people that are going to miss like 2 weeks in the future, do you recommend they watch your last lectures?
No, I usually say just stay caught up on my recordings, but I've had a number of students that will get ahead of them ahead of class and watch lectures. And then he found that the video that he watched and the class that I ran weren't in sync. I like did things at a different pace. That's the comment I hear the most, is that people that go and watch my old lectures, they'll be like, wow, you taught the same thing so differently. For better or for worse. Don't know. Oh, sorry, you can't see it. Maybe. I hope so. That's the goal.
You gotta be improving. Ron's a great professor. I mean, how many classes does he have?
I would guess hundreds. Oh, okay. You know, I was wondering why you didn't say the name correctly. I was like, that's not benzaldehyde. All right, in this, I would say it's important that we work forward and backwards, right? I think mapping the carbons, maybe not necessary here. So here's a version of this, just so that we can work on it together, something new. I obviously don't know what to do with that starting material. There's so many things I could do. Do I want to make an acetal? Do I want to make an alcohol? Do I want to make a carboxylic acid? Do I want to make an imine? There's a lot of things I can do, so I'm going to start by working backwards. What functional group do I have at the end here? Amine. And we have not seen that many ways to form amines. By the way, one of my OCHEM 1 students is making a table of reactions this weekend to prepare for her final. She said that she's color coordinating the table